And this picture looks like the best example of a cat that is both dead and alive at the same time. And there's lots of magic around it. And I think this is because we really try to over-analogize, and we try to make an analogy for what quantum is, and we don't experience quantum effects. So rather than make an analogy, I would rather try and be very precise of what is different, and then try and show through some examples. So quantum computing is very much like classical computing. You have to initialize your system, you have to go do some operations, we call them gates, and then you have to extract information. We call this measurement. But there's two things that are very different. And the first is this concept that something that is in a definite state can still behave randomly. Okay, that sounds a bit strange, but I'll try and show later. The second is that two things that are too far apart and they're individually random, so they have no information in them. Their correlation, when you bring them together, can have more information. So the whole is much harder, bigger than the parts. So let's try and demonstrate the first one. The only way I know how, by coming up with a simple coin flip experiment and then doing it through Qiskit. So first, we're going to import all the things that are needed. So here's a simple circuit. This circuit starts by declaring a quantum register, a classical register of size 1, and then it declares a quantum circuit, and then it applies this operation, which I'm just going to call the coin flip for a moment. Then it measures, and then we look at the results. So what's happening here is first we're initializing at 0, and this coin flip is making a mixture of both 0 and 1. So if I was to do this 1,000 times, you get about 50-50 that it's in either of them. So if I was to do this twice, how many people who raise their hands would expect 50-50? Obviously no one, so everyone's a quantum expert, which is really good. Oops. So if you do this twice, what happens is it's 100% always in the 0 state. So this operation isn't random. So this superposition of 0 and 1 became all 0 again. And this is a negative sign. So in quantum, you have this ability that future operations can cancel the previous ones through adding them together to give a negative. Or you can think of this as a different way. You can think of this final part as measuring it in a different basis, and you're asking the question, is the top of the circuit in 0 plus 1 or 0 minus 1? And you find the answer says it's in 0, 1. And then you can do things like introduce a phase flip, which simply is another operator, and that flips it in the phase, so now I've made the superposition of 0 minus 1, and I measure it, and I find that it's perfectly deterministic. So depending on how we look at it, even though it's in a definite state, sometimes it's random, sometimes it's not. And that's the first principle. The second principle is much more harder, and that's entanglement. So here's an example of a circuit. It's the same circuit at the top, but now I'm just adding a simple CX operator to it. And what this is we call it as a controlled knot. If the qubit is in 0, I'm going to flip the second. Sorry, if the first qubit is in 1, I'm going to flip the second qubit. Okay. So here we'll take it and we'll measure just in the individual one. So I made this state. It doesn't matter what it is, and I look at it and I measure it individually, and I find that it's random. So I find again that the first qubit is always in 0, but the second is in 0 and 1, okay? So it's not either in 0 or 1. If I go and measure it in this X basis and ask is it a superposition, I find that it's not a superposition. Any basis I try to look at it, it never has any information. It is always random. However, and the same is true for the second one. However, if I measure both of them, and I just measure both qubits, now it's still random, but they're perfectly correlated in this randomness. So the 0, 1 is perfect. If I measure 0 on the first qubit, it's 0 on the second, and vice versa for 1, 1. And now if I do and look in the superposition basis, I also find it's perfectly correlated in superposition. So the complete system has much more information than the individual systems. And this is entanglement. And if we wanted to run this and to show that we can do it live and run it on a real experiment in the lab. Here, all I've done is simply change the back end to a real device, and now I've set it up, it's pending, it's running the job in New York, it's going down into the cryostat, measuring it, and then in a second it'll come back. We're still waiting, so usually it takes about 30 seconds. So it's going down, it's getting measured, it's going to the cryostat, it's coming back up, we're processing information, and we're sending it back, and we find that if we run it on the experiment, we see that it's still perfectly correlated. There's a little bit of noise. This is because this is a real device, but you can go and explore and try these ideas yourself. So, entanglement is the resource that you don't have classically. Because the whole is much more powerful, much more bigger than the parts, it takes a lot to represent that. And so, many of you are probably wondering, what do we do with these machines, or how do we actually use them? The other part of Qiskit, which I don't have time to go into, is Qiskit Aqua. And this is the part that we're trying to build these early algorithms into it. So this entanglement is so rich that it's very hard to mimic classically. And the applications that first come to our mind is simulating nature itself. Nature requires entanglement to explain why electrons interact. So if I can come up with a way to control this entanglement, then I can go and simulate nature more efficient. We know our classical machines, the biggest ones that we can make, will bottom out at about 50 electrons or something like that to do an exact simulation. The second one is, I'm not going to say it's going to change artificial intelligence or anything like that, but what we have access to is we access to feature spaces that if you were to go mimic them on your classical machine, would take exponential resources to simulate. So what we're exploring is how do we take this quantum data and we extend it up into this entangled space, do the classification and project it back down. And we've shown recently in a paper that by simply adding more and more of this entanglement resource, we can get better classification for this toy data. And the third, which is probably at most only ever going to have a polynomial speed up, is exploring different optimization problems. And so you can use the entanglement to explore these in different ways. I want to finish by saying that we're committed to our community. Here's a video showing all the people that have actually used the quantum experience, the two public devices over the last week. So far, there's about 100 different papers in scientific journals using the machines that we've built. And we are actively trying to build a community and make quantum computing possible. Please follow us on these things and come talk to me at the booth later if you're interested, and thanks.
Fantastic. I am actually myself, and Kelsey, particularly backstage, is really now feeling a lot better that Jay knows how to get Ant-Man out of the quantum realm.